The students in our classroom have been examining physical changes, phase changes, and intermolecular forces. Some great examples of phase changes can be shown with the use of liquid nitrogen. And to help demonstrate, I've got a special guest from Atlanta's Fernbank Science Center, Adrian Elliott. Thank you so much for joining me, Adrian.
Thank you for having me.
Nitrogen is in its gaseous phase at room temperature. If we cooled nitrogen to its condensation point, which is minus 196 degrees Celsius, we'd have liquid nitrogen. Now we're going to do a really cool demonstration with Mr. Elliott's help. So tell me what we're looking at here.
Here we have liquid nitrogen. Like you said, its temperature is negative 196 degrees Celsius. It is cooled, but it boils at normal room temperature.
Look at that. It's boiling. Now, do we need to be nervous about the fumes that are coming off of that?
Not at all. Nitrogen just happens to be the most abundant gas in the atmosphere at 78%.
Of course. Now, that's really cool, but what else can you show us? What can we see about phase changes in liquid nitrogen?
I'm glad you asked. Here we have a metal bowl and some warm water. This will help us show a very important phase change.
Okay.
Let me pour a bit of the liquid nitrogen in here and let's
Wow.
observe.
Look at that. Now, what are we seeing here?
This is the phase change condensation. Here we have cold nitrogen boiling up together with taking some cold water. But once it touches warm water vapor in the air, it slows down those particles to produce small droplets of water. These small droplets of water will appear as white cloud, this white cloud that we see. And it's very dense, as you can see, as it falls off the table.
So we're seeing the phase change from gas to liquid.
Correct.
That's very exciting.
Correct.
Now, I notice you've got several things over here to show us a few more phase changes. What have you got for us?
Well, what I'm going to do is move this across to the side so we have a little bit more room to play with. And I'm going to hand these two to you.
Okay.
A banana. And I'm going to put this duo of liquid nitrogen here.
And just right in here.
Yes, please.
Okay.
Good job.
Well, I'm very excited to see what happens, but I'm very impatient. Do you have anything else over there that's a little smaller that might go a little faster than the liquid nitrogen?
Okay, let's add a few more things. Here I have a flour, which I will also put in there. Now,
Okay.
let me first of all describe what's happening with this banana. This banana consists of solid particles as well as water, which is inside of the banana.
Sure.
When I place it into liquid nitrogen at negative 196 degrees Celsius, it slows down the particles. The water has a particular property which we'll examine. Here we have a small flour. We're also going to put into the liquid nitrogen.
I'd like to point out you're using tongs, we're wearing our safety goggles, we're following the good lab procedures here.
Correct. Now, as we place this in, it's not going to take too long at all.
Okay.
Now, we're going to pull it out. Let's see what happens.
It looks the same.
But
Look at that. Totally shatters. So the liquid in that has now turned to solid and made it more
exactly,
dense.
within the space of just a few seconds, the petals of those flowers have turned to solid and shatter pretty much like glass.
Now, that gives me an idea about what might be happening with the banana in here, but I just can't wait to see it. Do you think it's ready?
I think it's ready.
Okay.
So we're going to pull this back a little bit. And what I'm going to do is I'm going to do this one, if it's okay with you. I'm going to take
Sure,
it out.
let's do.
And let's observe what happens if I hit it gently on the table.
Broke right in two. Totally solid.
Yes, at this point, the water also contained in here is frozen. So, what do you think has happened to the cells? All
Well, and we have a banana that we did, 20 to 30 minutes ago maybe, and you can see the long-term results of having been in that liquid nitrogen. We're seeing that browning there.
exactly. This banana, all its cells have died, so this browning indicates that the cells are no more. So when you see your bananas at home and they're brown, that's what happens.
Very interesting. Now, I'm curious, you've brought some balloons with you of all kinds. What are we going to see with the balloons?
Okay, let me move this to the side right here. Okay, it's not that cool. Now, with these balloons, I have brought an orange one. And let me first explain what's inside of this balloon. Here we have air, and the air is basically having a lot of kinetic energy. It's hitting on the inside of the balloon. What would happen if I were to take this balloon and put it into nitrogen? We're going to investigate. But before we do that, there's something students enjoy seeing. I know this is for high school, but usually the middle school students enjoy seeing when I show that a gas can take any shape by making a balloon animal.
Who doesn't love a balloon animal?
Okay, so I'll go ahead. So what I'm gonna do, show that this gas in here can take any shape, has a lot of kinetic energy, it moves around constantly. And what I'm gonna do is make a little puppy right here.
Now that's impressive. Good job.
Okay, thank you. Now what we're gonna do, I'm gonna take this puppy, inflatable puppy, and I'm gonna place him in liquid nitrogen. Now to do that, what I'm gonna do is take these tongs, these safety tongs, and I'm gonna add the puppy.
Important to point out that no animals were actually harmed in this investigation.
Correct. No animals at all. So as we place it in, it doesn't take that long.
Making a lot of noise in there.
And what I'm gonna do is take him out right now.
Totally deflated, but it's not staying that way.
Exactly. Let's observe.
Look at that.
When we placed it in, the gas that possessed a lot of kinetic energy constantly moved and gave the balloon its size. But once we placed it in the liquid nitrogen at negative 196 degrees Celsius, we slowed those gas particles down and we underwent a few phase changes. One going from a gas to a liquid, which we call condensation, and then a liquid to a solid, which was freezing. On taking it out, it went from a solid to liquid to gas and increased in size. But when it was small, that was because the atmospheric pressure, in fact, crushed it when it was a solid and a liquid.
Let me pull that and reverse that process.
Correct.
Now, that's so fascinating, but it all happened kind of in this canister. Is the way for you to show us what was going on in there?
I will. Here we have just one of these long balloons again, but here, what I'm gonna do is place this balloon into the nitrogen, and let's observe what happens. Let's take a look at it. What's happening?
Look at that. You can see it deflating all the way down.
It's going all the way down as the gas goes from a gas to a liquid to a solid.
And that atmospheric pressure again.
Crushes it.
Right.
Right? And on taking it out, let's observe what happens.
And again, it reinflates.
It goes from a gas to liquid to solid. In fact, you see me here pouring some of the liquid
Yes, you
to the
can-
tip
you
of
can
the
see,
balloon,
yeah.
and it's going a lot faster than it did before. Okay?
That. And now you also have helium balloons. What can you show us with the helium balloons and liquid nitrogen?
The helium balloons are right here. What I'm going to do is first of all move this to the side, right here, and I'm going to take one of these balloons and then I'm going to pour a bit of nitrogen on here. We remember that the gas helium that's in here has a lot of kinetic energy.
So the balloons are floating.
Exactly.
Okay.
And they're all spread out. Let's see what happens if we reduce the temperature of these gases inside of these balloons.
Okay. We've been watching it deflate, just like the other balloons. But will it rise again?
And let's see. Right now,
Look at that. As soon as
There.
it comes back up to room temperature, it's back in the air.
it's back in the air again.
That's great.
Because before we've slowed down those particles, brought them together, it became more dense and didn't float. Once the gas warms up, spreads out, it floats one more time.
Now, our students have been learning about intermolecular forces. So, what does all this demonstrate to us about intermolecular forces?
Well, let's take a look at what we played with today. Here we have water. Here we had liquid nitrogen. The liquid nitrogen boils at normal room temperature. The water does not. The water's intermolecular forces, namely hydrogen bonds, and the liquid nitrogen has mostly dipole-dipole interactions, which are quite weak.
Now, dipole-dipole interactions is something that'll come up in a couple of units, so stay tuned for that. Just remember that phrase for now.
Okay.
Now, one more thing, just for fun. I see you've got a racquetball over there.
Yes, I do.
I'm very curious.
Okay, I may need your assistance with this.
You've got it.
What I'm going to do is take that racquetball and first of all, place it in the liquid nitrogen.
Okay. And this is a normal racquetball that bounces like normal, everything we expect from a racquetball.
Correct. And if this racquetball, which is usually bouncing, in fact, I should have taken it out a little bit more. You can see it bouncing, right?
It's already gotten a little harder.
Exactly. Now, let's place it in. And let's leave it there just for about a little less than a minute.
Okay.
And we're going to take it out, number one, and see if it bounces, if it still bounces. Your rule will be to use this.
Oh my, it's an important scientific tool, the hammer. I'm very excited.
Exactly. So here we've left it for just a little while. Once we reduce the temperature of these particles, what happens? The motion is not going to be as much as it was before. So let's see what happens when we take this ball out. And what I'm going to ask you to do is to hit this ball with the hammer.
Okay.
And I'm going to hold it with these tongs, not my hands.
That's a good idea. My aim isn't that good.
All right. Let's take a look at the bounce.
Definitely changed on that front.
Now I'm going to hold it in place
Okay.
right here.
I can't wait. Let's see what happens. Totally shatters. That's awesome.
One perfect hit.
Well, if that doesn't show phase changes, I don't know what does.
Yes, so these particles are really, really dense and made the ball extremely brittle.
Great. Well, thank you so much for joining us. We've learned so much about phase changes using your friend liquid nitrogen. I appreciate you being here.
Thank you for having me.
Now that you've seen some extraordinary phase changes in liquid nitrogen, let's go back to our classroom so our teacher and students can show us a phase change you may have thought was impossible.
Now, let's look at a very different phase change called sublimation. Do you think that a substance can go directly from a solid to a gas?
No, it has to become a liquid first.
That's often the case, but in some special instances, a solid can transition into a gas without becoming a liquid at all. That phase change is called sublimation. Let me ask you guys a question. What do you see?
That's dry ice.
What is dry ice anyway?
Dry ice is frozen solid carbon dioxide. Its freezing point is minus 78 degrees Celsius. And what you see is the dry ice cooling the water vapor from the room and forming clouds. Watch when I put this piece of dry ice into the water. Now, you see the bubbles forming? You are seeing the dry ice changing directly from a solid into a gas without ever entering the liquid phase. And again, this phase change is called sublimation. Sublimation occurs when a solid turns directly into a gas without going through a liquid phase. Now, keep in mind there aren't too many examples of substances that we see doing this in our everyday life, but dry ice is definitely one of them.
Yeah, I've seen it at concerts.
And I think outdoor ice cream vendors use that as well.
Exactly. And sublimation can even happen with normal ice in your home freezer. See, over time, ice cubes get smaller because they're going through sublimation as the particles of water move into the air without even going into the liquid phase. Another substance that can change directly from a solid to a gas is iodine. Now, as you can see in this video, iodine is a solid purple crystal at room temperature. But if you put a small amount into a beaker and heat it on a hot plate as it undergoes a phase change, as it heats up, think about what usually happens when you heat a solid.
Solids usually melt into liquids.
Iodine isn't melting, it's turning into a purple gas without turning into a liquid first.
Right, that is sublimation. By the way, if we were sublimating iodine in our classroom, we'd want to use a fume hood so we wouldn't breathe in the vapors that are produced. The fume hood uses special fans to move vapor outside away from the laboratory. Remember that we always want to put safety first. Now, look at what happens when we put some ice cubes in a Florence flask. Look at the bottom of the flask. Do you see the purple crystals forming? Just like the solid iodine doesn't turn into a liquid when heated, the gaseous iodine doesn't turn into a liquid when it's cooled.
So what do you call it when a substance goes from a gas to a solid?
That's called deposition. And that's what you see happening as solid iodine crystals form at the bottom of the flask. Deposition occurs when a gas changes directly into a solid. It's the exact opposite of sublimation. One of the most beautiful examples of deposition here on Earth is the formation of snowflake crystals and frost. Snow forms as water vapor freezes directly into solid ice crystals on the surface of tiny particles in the air. Those of you who are familiar with planetary science may also be very familiar with sublimation. Now, where other than Earth can sublimation or carbon dioxide be seen in large amounts?
I remember that Mars has a polar ice cap made of solid carbon dioxide.
You're right. And Mars also has a very thin atmosphere, making it difficult for liquid to form on the surface. So, what happens to that Mars polar ice cap when it warms up a little bit?
It goes to sublimation and changes directly from a solid to a gas. That must be why the polar ice caps change shape and size depending on the seasons.
You got it. And since comets have a lot of solid carbon dioxide and water in them, what happens as they get close to the sun?
Oh, is that where that giant comet tail comes from? I've seen those.
Exactly. The comet's tail is partly made up of carbon dioxide, gas being released from sublimation of solid carbon dioxide. So what are the major phases of matter?
Solid, liquid, and gas.
Good. And what phase transitions have we discussed?
Evaporation.
Okay, and now what happens in that phase transition?
A liquid turns into a gas.
The reverse is condensation.
Good. Any others?
The other phase change we discussed was melting, where a solid goes into a liquid phase. The reverse of that phase transition is freezing.
We also talked about how a gas can go straight to a solid phase, and that's called deposition.
The reverse of that is sublimation. That's where a solid transitions directly into a gas phase.
Great job. These are all phase changes or transitions that we discussed.
If you want to learn even more about phase changes, go to the toolkit for Unit 2, where we give you instructions on how to design and carry out an investigation that demonstrates how intermolecular forces cause different liquids to evaporate at different temperatures. And you can examine why some solids melt at lower temperatures, while others melt at high temperatures. The phase transitions you just learned about are all physical changes. Whether freezing, melting, or vaporizing, materials still stay the same chemically. But you need to learn about the different ways that substances change chemically. So we'll look at chemical changes in the next video on the playlist. See you there.